Staying a little bit away from the microphone now. Yeah, welcome here again in the wastewater treatment session in Brooklyn 1. Now we have a Zoom presentation and we're getting really asked if you can come to the middle and congregate here in the middle, because we have a Zoom and camera sitting up here that Miriam can see you as well. That would be excellent if that would be possible. I forgot as well to introduce myself at the start. So my name is Ulrich Glasner. I'm working for Queenstown Lakes District Council and I'm sharing that session for you today. So Miriam will come online via Zoom at 2:45. Miriam Weissroth is working for WEHRLE Umwelt GmbH. Her topic is membrane process for the treatment of leachate from landfills. Miriam is holding Master of Science in Biology and Ecology at the Technical University of Darmstadt in Germany. She studies of ecology and environmental chemistry at the University of Edinburgh in Scotland, and she is holding a PhD at the Faculty of Soil Science of the University of Munich on peel losses with surface runoff from agricultural lands. Miriam worked as a consultant in the fields of water supply, water quality, groundwater remediation, and since 2006 she's working for WEHRLE, working with heavily polluted industrial effluents and leachate. So I tried to push the right button to get her online.
Good afternoon, everybody. My name is Miriam Weissroth, and I'm speaking to you from Germany. I'm very sorry that I can't be with you at the conference today, but I suppose it can't be helped. But I thank Water New Zealand very, very much for giving me the opportunity to present online. Now, I would like to talk about membrane processes for the treatment of leachate from landfills. And before I actually get started, I would just like to say a few words about WEHRLE, the company I work for, and a few words about leachate to give those amongst you who may not be so familiar with leachate a little background, and then I'll move on to the membrane processes. Okay, so WEHRLE is a family-owned company, and we supply effluent treatment systems, and we are located in the southwest of Germany, very near to France and Switzerland and Austria. We just hop over into these countries. And we've been around for a very long time and are a pretty small company that has specialized on the treatment of industrial effluents and heavily polluted wastewaters. And the way we go on about it for our clients is that we have a technology portfolio from which we choose, and we combine different processes to actually achieve what the client has asked for. So we have a pretty good overview which process technology works where, and we are always on the lookout for new technologies to come into our portfolio. That's enough about WEHRLE. I would now like a few words about leachate, and that means leachate has different origins. I mean, you're all aware of leachate coming out of landfills, but then there are leachates that come from the storage of waste or waste handling, waste transport, and also the water coming from the waste treatment plants is considered to be leachate. And consequently, having different origins, we have different compositions. And you see here a wide range of COD and TKN values. And you see it's really heavily polluted stuff that we talk about. But leachate quality does not only depend on its origin, it also depends on the landfill type of waste. So that is what you and I throw away and actually ends up on a landfill. And of course, it also depends on the waste management strategies that a region, a country, a continent has. Do we deposit fresh waste, pre-treated waste? Do we separate it upfront to landfilling? And. And there are many more factors that influence the leachate quality. For example, seasonal changes. Is it hot and dry? Do we have a lot of rain? We have aging processes in the landfill itself. So we have many factors influencing leachate quality, and they're superimposing each other, and. So you could rather say that leachate is a collective term for a variety of highly variable liquids. Now, when we talk about leachate treatment, we have, of course, to look at the treatment targets, and that they vary from site to site is understood. But I would like to point out that when looking back, we see a great evolution in treatment targets. It all started in the 70s, and they only looked at COD and ammonia at the time. Those were measured in grams or milligrams, and then people became aware that there is a lot of harmful stuff coming out of a landfill, and more parameters were monitored, such as, for example, heavy metals or AOX or the polycyclic aromatic carbons, the aromatic carbons, and so on. And today we are looking at PFAS and BPPA, and we have reached a level where we measure substances in micrograms per liter or nanograms. And of course, that has an impact on the processes that we need to treat the leachates. And I would like to point out that today we also look at salt removal. That is something that was not looked at in former times, so that's fairly recent that we find salt removal requisitions. But when we look at leachate treatment, we have, of course, also to look at the local conditions. What do we find at the site, and what budget do we have? Is chemical supply sufficient, power supply sufficient? Do we have personnel, etc., etc.? And last but not least, we have to consider what's the hydraulic volume that needs to be treated. It ranges from very tiny to very large, and naturally you wouldn't like to treat 5,000 cubes per day using evaporation. I presume, at least, you wouldn't like to. So now looking at the treatment processes, SWANA, the Solid Waste Association of North America, has written a wonderful report, and in that they list 28 processes for leachate treatment, and among them membrane bioreactors and reverse osmosis. So 2 out of 28 are membrane processes. So the question would be, when would I use a membrane process and when would I use one of the others? And my answer to that is, if you target a high removal of organics, of nitrogen and solids, you should go for a membrane process. And if you target high treatment levels and large volumes are involved. Now, just as a reminder for those who perhaps do not work with membranes every day, we differentiate between 2 main types of membranes. We have the porous ones that we use to retain solids, and that are microfiltration and ultrafiltration. And we have the non-porous ones, the nanofiltration, a reverse osmosis type, and they help us to retain dissolved compounds. I'd like to start with the ultrafiltration. Now, looking at leachate treatment, what do I do with the ultrafiltration? I would combine it with a biology to form a membrane bioreactor. And I've seen in the program that there are several presentations about membrane bioreactors, so I feel I don't have to really say a lot about them. What you get is a very compact system. You can see that on the picture on the right. You have the very compact bioreactors in the back, and you have the ultrafiltration in the front. But what difference does it make to use an ultrafiltration? Of course, we retain all the biomass, and that means we have a far higher MLSS inside the reactor than we would normally have. We get easily up to 15-20 grams per liter, and that means the reactors become very compact. We can control the sludge age and keep it well above 20 days, and that, together with the compact bioreactors, which maintain a temperature between 30 and 35 degrees, gives us a very good, or maximal, I should say, COD removal and a stable, complete nitrification. And another asset to the ultrafiltration is that when we have to target secondary treatments, we have the advantage that there are no solids in the effluent. Okay, but what precisely does it do for us in leachate treatment? A membrane bioreactor removes all the organics that can be removed. It removes around 90–95% of the nitrogen. It retains all the solids, but it doesn't do much on the salt side, and it doesn't do very much on the trace organic compounds, or let's say the harmful substances, I would rather say. What leaves the MBR is the recalcitrant COD and salts and TROC. And just to show you some results from leachate treatment plants, this is the same plant, and you can see that the COD in the feed is between 10 and 25,000 milligrams per liter. The design was for 6,600, that's the red line. And you see that the effluent COD, the blue dots, are fairly constant, around 2,000, 3,000 milligrams per liter. And that is the hard COD, the recalcitrant COD, that cannot be removed by any biological process at all. On the right, you see the ammonia. There you may notice it also varies greatly between 1,000, 5,000 milligrams per liter. And on the right hand, you see the scale for the ammonia concentrations in the permit. And you can see it's consistently below 2 milligrams per liter, apart from a few outliers where it goes up to 10 milligrams per liter. So we see an excellent nitrification. And that means basically the MBR can serve as the plow horse in a leachate treatment plant. But what do you do if it's not enough? If you just want to remove some of the recalcitrant COD, you might want to use activated carbon if you have it, because that is a thing that's not available in all countries. And it also takes out your COD or reduces your COD. It doesn't do very much on the other parameters. So most likely it's not enough these days in terms of leachate treatment, and you would want to look at something else. One option could be a nanofiltration, and I would like to dwell a bit longer on the nanofiltration because it's not so well known to most people. It's the small brother of a reverse osmosis. It has pretty much the same setup, but different membrane characteristics that makes it very interesting for us. It removes a good part of the COD. It doesn't do much on the nitrogen side. It removes part of the salts, mostly the multivalent ions, and it removes some of the harmful substances. Now, but it leaves us with a concentrate because, after all, it's a membrane process and all of them just divide into clean and dirty. So we have concentrate, but because the yield is pretty high, 85 to 90%, that only leaves us with a small concentrate volume. I'd like to show you some results from a nanofiltration. This is from a longer trial, or from a trial run, and you can see that we fed the nanofiltration on site with 5,000 milligrams per liter of COD, and we had consistently permit concentrations around 10 milligrams per liter. So the removal of COD is pretty good, quite satisfying, I think. The interesting thing about the nanofiltration is that it has a comparatively low retention for salts. What you see is that the feed concentration to the nanofiltration and the concentrations in the permeate are about the same, which means we have no noticeable retention of the chloride, and that applies to many of the ions. And for that reason, we would find a low osmotic pressure because, we don't have a buildup of salts on the concentrate side. So that's the blue triangles at the bottom. And we can reach highest yields of about 90%. Those are the red squares on the top line, and that's the right axis. So this is a very promising approach, I think, to leachate treatment. But still, we do have the concentrates. And we propose, if possible, to combine that now with activated carbon to get rid of the concentrates. So this means we take the nanofiltration concentrates, lead it via activated carbon, and return it into the biology and have nothing left then. That gives us pretty much the same treated leachate qualities that we have with a pure nanofiltration, but it removes us or removes the problem of the concentrate treatment. The only real drawback is that you need granular activated carbon, and that is not to be had in all countries. I would like to share some results from these biomembrane plus systems, from these closed loop systems with you. When we look at, how shall I say, well-known or conventional parameters such as chromium for the heavy metals, or AOX, or fish embryo toxicity, we see that the NF permit with regards to the leachate feed concentrations and the target concentrations, or what we want to reach, the NF permit quality is very good, so we can safely meet our treatment targets for all these parameters. So they do the nanofiltration in combination with membrane bioreactor and activated carbon does a great job. Now, I would like to show you some more detailed results. What we have here is a herbicide. It's called 2,4-dichlorphenoxyacetic acid. You see it's a rather small molecule, and we fed it into a bioreactor. I look at the columns now from the left to the right. You see the raw effluent had a concentration of around 100,000 micrograms per liter. And that remains pretty stable. We had no accumulation in the activated sludge. And over a couple of weeks, we did not see any changes in UF permit, which means 2,4-D simply passed the membrane bioreactor. It didn't do anything in there. Nothing happened to it. But the membranes retained it. About 99% could be retained by a nanofiltration. And the concentrates were then treated with activated carbon. And we see that the concentration after the activated carbon is really low, so it absorbs very well to the activated carbon. Another example is glyphosate. I'm sure you heard that name, and its main derivative, AMPA, also very small molecules. We also set the membrane bioreactor with a concentration of about 100,000 micrograms per liter. And we see we had little AMPA in that solution. And the glyphosate is pretty much biodegraded in the biology. Glyphosate are the green columns, and AMPA accumulates, so that increases. But when we look at the AMPA concentrations, we see it's around 30,000 micrograms per liter. So we feed in 100,000 of glyphosate, and we have 30,000 of AMPA, which means we have removed about 2/3 of it by the biology. The nanofiltration does a quite good job in retaining both glyphosate and AMPA, but we can see that AMPA does not absorb so very well to activated carbon. So we have quite different behaviors here. Another example is PFAS in a biomembrane plus plant. We are just starting to look at PFAS over here in Germany. We've been watching it for a long time, but we have not really started to tackle it. Not we as WEHRLE, but we as a country, so to say, but that is changing now. And we have an official trial for a municipality going on at the present. It's still continuing, so I don't have the final results yet, but I want to share these preliminary results with you. Orange lines are what goes into the bioreactor, and gray is what comes out of it. And for PFOA and H4PFOS, you see that the bioreactor removes quite a large proportion of it. Then the nanofiltration does a good job as well. That's the blue line is the NF permit. But when we look at PFOA, you see we don't meet the treatment target because that's the red line at the bottom. And just recently, we changed the nanofiltration membrane. We use another one now, and we are getting closer. We're not quite there yet, but we hope to meet it. But for the H4PFOS, we see we can actually safely fulfill treatment targets, so that gives us hope. Just wanting to say that this combination is very promising, but it's not a panacea. It can't achieve all. If you need even higher treatment results, you must go to reverse osmosis. We all know we can feed leachate directly to reverse osmosis. You get excellent results, no question. The only thing you have to watch, that is the ammonia, because on leachate we have these very high feed concentrations and we have a comparatively high slip of ammonia over a membrane. So we might find easily 10, 20, 30 milligrams of ammonia in an RO leachate, treated leachate. The missing removal of the organics puts a stress on the membranes and it reduces the overall effectivity. So the yield is not so very high, let's say 60, 70%. That leaves us with about 30% of concentrate, meaning 1/3 of our leachate ends up as concentrate. And this concentrate is really, really dirty, which makes concentrate treatment, e.g. In an evaporator, more difficult. But it's not so very expensive. So now, most people ask themselves, what do I do with a concentrate? And in many countries, the usual way of dealing with it is we just bring it back to the landfill. The only problem is I see it all again over and over. It starts to accumulate. Every molecule I check out with a lot of pain and effort, I see again, and I see its brothers. So it doesn't really help me in the long run. This is these are graphs from a landfill site that started to return the concentrate back to the landfill, and you see practically immediately the COD and the ammonia start increasing, and so does the conductivity as the indicator for the salts. And naturally, that means the overall yield of a reverse osmosis will drop fairly soon, within a few years, because the osmotic pressure increases and the effectivity simply reduces. So if you ask me, I think the best option to deal with leachate and get the highest quality is to combine the biology and the reverse osmosis, because that gives you the best results. You get a fairly small concentrate amount, and that concentrate does not contain any ammonia any longer and has lost the fouling potential of the COD, no volatile compounds there any longer, so it doesn't smell. And you can easily, or comparatively easily, treat it by an evaporator, and the condensate can be mixed in with a treated leachate. Whereas when you have a reverse osmosis without biology, the condensate is very dirty stuff because it contains all the ammonia and a lot of the volatile compounds. So this would be the recommendation. Now, the question to when to use membrane processes, I think, has been answered, or I hope it has been answered. Now, you might be asking the question, but when not to use membrane processes. And of course, I would say when you have low or lower treatment targets, you don't have to, and you don't want to go to membrane processes. If an MBBR does the job, it does the job, and that's it. If you have a small hydraulic volume of, let's say, 50 cubes or less, you probably would not look for a membrane bioreactor because it gets comparatively expensive. But you might be looking for a reverse osmosis only. And if you have a low budget, then again, you don't want to go for a membrane bioreactor or its combinations, but perhaps you might consider a reverse osmosis only. And I'm coming to the end of my presentation just to show you, this is a tiny reverse osmosis, 15 cubes, and you see it's a tiny containerized unit, very small. This is a very large installation for 5,200 cubes per day, and what you can see in the pictures is that you can just multiply the ultrafiltration, so you can upscale membrane bioreactors very easily, and you can really use them to treat immense or large volumes when it comes to difficult wastewater, large volumes. I mean, for a normal municipal wastewater treatment plant, that is, of course, a small volume, I know that. And in the middle, you find clients who prefer the reverse osmosis, like this one, or you would have clients that go for a membrane bioreactor because they say, I'd do anything to avoid the concentrate. So there is a range in the middle where the client just has to decide for himself what's best for him. And I've come to the end of my presentation. I thank you very much for your attention, and I hope to meet you all next year.
I have to put the mic on. Here, thank you very much, Miriam. What I heard, you are in Germany at the moment. Is that correct?
Yes, can you hear me now?
Yeah, we can hear you, and
Yeah,
I think
yeah.
it's 3:15 in the morning in Germany at the
It's,
moment, only to let you know
just
that.
my best time of the day, so to say. Not quite, yes. But
Well done with
hello,
this.
everybody.
Yeah, well done with this presentation. So, any questions from the floor? Please spell your or put your name up and your affiliation, please. Thanks.
Hi Miriam, thank you for that, and thank you for getting up early. Matt from Apex Environmental. One of the problems with landfill leachate, one of the many problems, is very high inorganic contamination. So do you need any special cleaning regimes for your membranes, or any special things you do to avoid inorganic scale and loss of flux due to scaling of the membranes?
You mean the ultrafiltration membranes, I take it? For the ultrafiltration, no, because you don't concentrate. You have no concentration on the salt side. So the ultrafiltration, no, it does not really suffer from inorganic stress, so to say. It's more the fouling or the viscosity that builds up that puts a stress on the membranes. But with the nanofiltration, the reverse osmosis, yes, of course. I mean, there you'd find it as you'd expect it. Does that answer your question?
Yes. Yep. Any further questions? Excellent.
Hi Miriam, Sarah Burgess here from the Ministry of Health. My question is, with the MBRs, what happens to the sludge from the biological reactor? Is it just returned to the landfill, or does it need special treatment as well?
In most cases, it's just dewatered and returned to the landfill to decompose any further. It does not need any special treatment. It's not considered to be hazardous or to contain germs or viruses or so. I've never heard of it having that somebody had to burn it, for example, or incinerate it, I should rather say. No, it usually is just returned to the landfill after dewatering.
Okay, thank you.
We have time for maybe 2 more questions. Maybe questions from me. What is the biggest challenge for you? You are working worldwide, and you have normally in each country and in the country itself different targets to achieve in regards of resource consent conditions. What is a challenge for you providing then treatment?
I think the biggest challenge at the beginning is really to find the optimal solution for the site, because some clients have very high treatment targets, but it's not realistic that they can meet them with what they have been given on site. It's, as I would say, I would not like to take a membrane bioreactor, which is a robust but yet a complex technology, into Central Africa, for example, because you don't have the boundary conditions. Like, you need a stable power supply, and you need really qualified personnel that's dedicated and stuff like that. So I find the most difficult thing is to find the right process for the special site, and to work that out with the client. And sometimes it's quite frustrating, because you know it won't be running. You know, you develop a concept that's really nice, but you know from experience it'll be turned off after a year or 2 because they can't be bothered, or they don't have the money. That is a huge problem. They can't afford the operation of a proper leachate treatment plant. So from my point of view, sometimes less would be more. I would rather have a simpler technology that keeps running and doesn't do a perfect job, but a good job, than having a perfect technology that's not working at all. So that's the most challenging thing in the end. Everything else can be arranged.
Thanks, Miriam. I'm totally with you on that. Any further questions? No. Here, thank you very much for turning up in the middle of the night, so to speak. And thanks for your presentation.
Very good.
Really good insights. So thanks very much, Miriam.
Thank you. Bye-bye then.
All the best. Bye.
Bye.